Shin-Yeh Tsai. So today I'm going to talk about our paper, A Double-Edged Sword, Security Threat and Opportunities in One-Sided Network Communication. This is a joint work with my advisor, Professor Yin Zhang. We are from Purdue University. So let me introduce the difference between the two-sided communication and one-sided communication to start this talk. I will use the key value store as an example. So in traditional two-sided communications, when user wants to set or get the request, it will send a request to a remote CPU. Once the CPU gets the request through the NIC, it will process with the memory to get the data and reply to the user. Similar to a get request for a set request, it's also send a request to the CPU through the NIC, access the memory to set the data, and act to the users. But this is different in one-sided communication model. So in one-sided communication, the CPU is totally bypassed. So when a request, it will go through the NIC and access the memory to get the data and return. Similar for a set request, it's also interact with the memory directly. So in this design, the CPU is totally bypassed at the remote side. So because of this design, the one-sided communication frequently offers like low latency, high throughput, and low CPU utilization. So because of this performance benefit, recently data center developers start considering to move one-sided communications into data center to improve the application's performance. So there are several implementations of one-sided communications, like the RDMA, OmniPath, or GenZ. So there are also several one-sided communication-based applications in both academia and industrial recently. However, most of them are either focusing on performance, scalability, or usability. So what about security? It's a really important factor in data center, especially data center is a multi-tenant environment. So before I go into the detail of today's talk, let me have a quick outline here. So today I will first introduce the vulnerability in one-sided communication in two aspects. The first aspect is the protocol, or I would say it's the primitive part. Then I will discuss the hardware that implements one-sided communications. Then I will introduce the opportunity. Actually, the one-sided communication also brings a chance to opportunity and to security. So it's indeed a double-edged sword. Then I will conclude today's talk. So the first vulnerability is one-sided communication lacks of accountability. So accountability is really important for a system or applications because it relies on accountabilities to pinpoint the attackers or find the root cause of a system crash, recover from a system crash. However, in one-sided communication, it lacks of accountabilities. For example, for the write accountabilities, issue the write request to a server side, but server side cannot tell who sets the record or even a corrupted record. So for read accountability, when user get the data from the server side could not tell who get the record. So read accountability is really important when server sides want to optimize the data structures because it needs to know which data has been accessed frequently. However, with one-sided communication, we no longer have these things. So after discussing the accountability, I will introduce the denial of service. We know that denial of service is also in two-sided communication model. However, it's worse in one-sided communication because it's really hard to trace the attackers now. So, and in order to complete the one-sided communication request, the network equipment and the network device need to cache a lot of metadata to complete the request. Therefore, you could see in this figure, different users occupies a part of resource inside the NIC. However, when the attackers comes in, it could easily overload the whole NICs to prevent others to access, to use the resources, or to hurt the performance. So this is the denial of service of the one-sided part. So how to mitigate these vulnerabilities? So the first idea is to adding an intermediate layer at the sender side. Because we know that even with one-sided communications, the sender side CPU is still involved. Therefore, we could add the intermediate layer at the sender side to do like a monitor, to check, for accountability, to see the traffic. And we could also enhance the smart NIC at the receiver side to check all the things, to handle all the things for the CPU. So after covering the vulnerability in the one-sided communication primitive, we also found that there are several vulnerabilities inside the hardware which implements the one-sided communications. So in this part, I will use RDMA as an example. So let me introduce the difference between the one-sided communication and two-sided communications hardware. So in a two-sided communication hardware, a request will first pass into a NIC, a regular NIC. Then the NIC will pass the request to the CPU. Then the processor or CPU will handle the address mapping, permission checking, and resource isolation, and access the memory. So in one-sided communications, there's no CPU. Therefore, the NIC, a bigger one, I would say a more powerful one or complicated one, needs to handle all the things. Resource isolation, permission checking. So in RDMA, we use a concept which is called memory region. So the server side has to first register memory space to get the memory region, and it will return one R key and L key and the address. Then the server side needs to pass this address to the remote side to let the user use these keys and address to access the memory space. However, we found out this key is actually predictable. So these keys are predictable, the hardware managed keys are predictable. It's a third vulnerabilities. So we found that in all three NICs we tested, the RDMA NICs from Mellanox, 3 generations, they all have the same issues. You can see these figures. The x-axis is the nth memory region register, and y-axis is the R key and L key values. So we found out that in the first 5,000 registrations, it's sequentially purely increasing. So X3, X4, and X5, they are all following the similar patterns. Therefore, the attacker can easily guess the key value, R key and L key values. So this is the third vulnerability. Let's move to the next one. So the side channel issue is also inside the NICs. So as what I mentioned above, the NICs now need to cache a lot of metadata to complete the one-sided request. Therefore, so it needs the key, the memory regions information, and also the page table entries to do the address translations. However, if all the data inside the NIC works well, if the NIC started thresh cannot hold all the metadata, it needs to fetch the metadata from the host machine. So these parts create the timing difference. You can see in this figure that this is a PDF figures. The x-axis is the latency, to the right-hand side is more greater latency. The y-axis is the percentile. So if all the data is inside on NIC SRAM, you can see it's really fast, it's a blue line. If the page table entry is missed on both SRAM, you need to fetch it from the host machine. It's a little bit longer. If all the metadata is not on the SRAM, you need to fetch all from the host machine. You can see there's a clean separation between these three assets. So this part creates the timing difference, a side channel. Therefore, the attacker can use this side channel to tell whether a victim has accessed a page or address before. So this part creates the side channel attacks. So based on this timing difference, we build a side channel attacks in RDMA. And we are going to present in the next month using security. So if you are interested in these side channel issues, please check our paper or visit our talk. So we really deploy these attacks on real applications. You can see the attacker can really guess the victim's access patterns. So let me discuss how to mitigate these issues. So the first one is the key. So because the key now generated is in sequentially patterns, the first way is to generate the memory registration keys cryptographically. So change the sequential to random. The second idea is to isolate the onboard resource for different clients or different users. Because once I isolate the resource, the side channels can be mitigated. Because the attacker cannot easily kick out the client's resource or the metadata. The third idea is to enhance the smart NIC at the receiver side to handle the keys and also the side channels. So after covering the side channel, after covering the vulnerabilities in one-sided communications, actually we found that we can also leverage to enhance the securities. So we know that with we observe that with one-sided communications, the server side cannot tell which part the client is accessing now. So this can help us prevent from one scenario that the server side is the attacker, wants to steal the access information from client side. And client has a lot of data hosted on the server, but don't want the server to learn which part is accessing by the client. So this is an attack scenario what ORAM or oblivious RAM have been designed to defend. So with the ORAM system, the clients need to perform a set of read-write operations to the server side. Like this tree, we use path ORAM in one message exchange to hide the real data blocks or real data that the clients want to access. So the server side cannot tell which part clients really want to access in because it's the full path. So instead of using a costly ORAN operations, a set of reroute operations with two-sided communication, we can actually leverage the one-sided communication to hide the access pattern because server side cannot see which part is accessing now. So with one-sided read, we get the green part data directly and return. So we modified the ORAN system to partially use the one-sided communication read for their ORAN read. And for the write, we still maintain the full ORAN protocols. So for all our design choice and also the detailed discussions, please check out our paper. We don't have time to cover it now. So we found out that even with partially modified ORAN system, we can still get good performance. The x-axis is the percentage of one-sided read operations, and the y-axis is the throughput. You can see the performance significantly increase once we increase the k% of the one-sided communication read. So let me conclude today's talks. So the PCL work, so our sectional works, the PCL work, and also this work is kind of the star work of the security in one-sided communications. So there are still several things can be explored. So we know that when data center developers, they start considering to use one-sided communication or RDMA in data centers, they should really be careful, or they should pay attention to the security concerns. So they start to using this one-sided communication because of the performance. However, once we deploy the security things or the protection into the one-sided communication, can we still have this performance of one-sided communication? Is this still attractive? So how to solve the trade-off between the performance and security is always a challenging question. So we think that we need the hardware vendors and software developers and also data center people to work together to find the best balance point between all the things. So this is my today's talk, and thank you very much. I'm happy to take questions now.
Hi, good morning. I'm Ivan from UBC. I thought the connection to ORAN was really interesting. I was wondering about the threat model in that case, because ORAN typically kind of assumes that the client doesn't trust the server. And so in your context, when you implement it using one-sided communication, it seems like the client has to assume that there's one-sided communication, right? But what if it was two-sided? Then it would actually reveal the access pattern to the CPU. So I'm wondering about the threat model, I guess, for the ORAN context.
Yeah, we choose the same original ORAN security guarantee, but this part is what you mentioned, that we didn't modify the write part. Are you asking about the write part? Because if we do the write, one-sided RDMA, as a one-sided communication write, the server side actually can see the difference. You can just checkpoint the whole memory to see which part is modified by the client.
Isn't that also a problem for the read?
For the read, because the data is not changed, therefore the server side cannot tell which part has been read.
But the client doesn't know that the server side can't see the next memory, or that it's all one-sided, right?
Yeah, it's all one-sided, so therefore the server side cannot see. Yeah.
One more question.
Hi, this is Shin-Yeh from Renton. So most of the attackers in this case, or probably all, will be only for the senders, right? It's a one-sided communication. The attackers will be senders. So making improvements or taking steps like the example of making some changes in CPU on the sender side, will they be helpful? Is it the sender itself is attacked?
I think it's still a solution because in data center, the hardware part is controlled by the data center developer or data center managers. Therefore, we could employ some dictionary library or even inside the kernel to force this management. Yes. So deploy at the sender side should still be considered. But I think at the receiver side, like enhancing a smart NIC would be a better solution.
All right, let's thank the speaker once again.